Heliopause, the boundary where the sun's solar wind finally loses its battle against the wider galaxy and enter true interstellar space, the region between stars. Every measurement before that date had been taken from inside our sun's protective bubble, a region dominated by hot, sparse plasma flowing outward from the sun itself. Every measurement since has come from somewhere no instrument had ever physically existed before, immersed in colder, denser plasma left behind by the death of ancient stars across the galaxy. If you did not know a human spacecraft was already living among the stars, smash that like button right now, because the data it just sent back is even stranger than that fact alone. Confirming that crossing was not simple, scientists could not just look out a window and see a line in space. Instead, they relied on an instrument called the Plasma Wave Subsystem, originally built decades earlier to study the radio emissions and electric fields of planets like Jupiter and Saturn during Voyager's grand tour of the outer solar system. That same instrument, repurposed for an entirely different job that nobody on the original design team could have anticipated, became the tool that finally proved Voyager had left the solar system. ON April 9th, 2013, the plasma wave instrument detected oscillations at a frequency of about 2.6 kilohertz triggered by a solar, earlier in March 2012, and only just reached Voyager's location after traveling outward through the heliosphere and beyond. That frequency corresponds directly to the density of free electrons in the surrounding plasma, an electron density roughly 80 times higher than scientists had measured just frequency, called the plasma frequency. That frequency depends on nothing except how densely packed the electrons are, following a precise mathematical relationship that physicists have understood and tested in laboratories on Earth for nearly a century. By measuring the frequency of these oscillations, scientists can calculate electron density without ever needing to physically scoop up a sample of the gas itself. It is one of the cleanest examples in all of astrophysics of using pure wave physics to measure something otherwise completely invisible, hundreds of millions of miles beyond direct human reach, turning a faint radio tone into a precise number for how many electrons occupy each cubic centimeter of space. For years after the 2012 crossing, this method only worked when the sun cooperated. Powerful solar eruptions send shock waves rippling outward through the solar system, and when one of those shocks eventually reaches Voyager 1's location in interstellar space, it triggers a brief, intense burst of plasma oscillations that the instrument can detect and measure. The problem is that these solar shocks take roughly a year or more to travel that far, meaning Voyager's map of interstellar density was being built from rare, fortuitous events, sometimes only once annually, leaving enormous gaps in the data. Like and subscribe if you think waiting an entire year between data points sounds painfully slow, because what scientists found next changed that completely. Researcher Stella Ocker and her colleagues went back through years of Voyager's plasma, wave recordings searching for something subtler than the occasional dramatic shock-triggered burst. What they found, starting from 2017 onward, was a persistent, much weaker narrowband signal that had been quietly present in the data the entire time, a continuous hum rather than an occasional shout, with a tone that rises and falls in step, with the density of the surrounding plasma exactly the way the older, shock-triggered signal had. Unlike the shock-triggered oscillations, this new signal did not require a solar storm to appear. It was simply always there, rising and falling gently, tracking the density of the surrounding interstellar plasma in real time, almost like discovering that a distant ocean has been making a constant, audible sound the whole time. If only someone had been listening closely enough. Researchers had to sift through years of wideband receiver data, recorded continuously since Voyager crossed the heliopause, to confidently isolate this weak signal from instrument noise, and confirm that it was a genuine physical feature of interstellar space itself, and not some artifact of the spacecraft's own aging electronics. This persistent hum let scientists do something they had never been able to do before, build a continuously sampled map of interstellar plasma density with measurements spaced roughly every 3 days across a span of about 10 astronomical units, instead of relying on rare yearly bursts. That map revealed something genuinely new, small-scale density fluctuations occurring on the scale of single astronomical units, a kind of fine turbulence rippling through the interstellar medium that the old, sparse method could never have detected. Subscribe if discovering an entirely new texture of the universe just from listening more carefully sounds as wild to you as it does to this channel. But here is where the real mystery enters, the part that brings quantum physics directly into the conversation. Scientists still do not know with total certainty exactly what physical process is generating this persistent narrowband emission in the first place. 2 leading explanations have been proposed, and both of them reach down into quantum-level behavior of plasma itself. The first possibility is called thermally excited plasma oscillation, where the natural heat energy of The interstellar plasma itself is enough to continuously jostle electrons into oscillating at their natural plasma frequency, without needing any external trigger like a solar shock at all. The second possibility is something called quasi-thermal noise, a subtler quantum statistical effect where the random thermal motion of countless individual electrons, each one behaving according to quantum mechanical uncertainty in its exact position and momentum, collectively produces a faint, continuous electromagnetic hum purely as a statistical byproduct of how charged particles fundamentally behave at extremely low densities. Quasi-thermal noise is not a hypothetical curiosity invented just for Voyager. It is a well-known and carefully modeled phenomenon in plasma physics, rooted in how quantum mechanics governs the behavior of individual charged particles, even when there are trillions of them spread across a region of space. Each electron does not move along a single, perfectly defined path the way a classical billiard ball would. Instead, quantum uncertainty smears out exactly where any single electron is likely to be at any given moment. And when you have an enormous swarm of electrons all behaving this way simultaneously, their combined motion produces tiny, unavoidable fluctuations in the electric field around them, fluctuations that can show up as exactly the kind of faint, persistent radio hum Voyager has been recording. This same quasi-thermal noise has been studied extensively in plasmas much closer to home, including the solar wind streaming past Earth, where dedicated spacecraft instruments have measured it directly and used it to cross-check other density measurements, giving physicists real confidence that the underlying theory is sound, even while the specific application to Voyager's interstellar signal remains unconfirmed. The challenge is that Voyager 1's antenna, while remarkably capable for instrument built in the 1970s, has real physical limitations. Its effective length is about 10 meters, with a width of just over a centimeter, simply too short to cleanly separate a true quasi-thermal noise signal from ordinary thermally excited oscillations using current data alone. The two mechanisms are expected to produce subtly different shapes in their frequency spectrum, with quasi-thermal noise theoretically showing a narrower, sharper peak right at T plasma frequency, while thermal excitation would tend to spread its energy across a somewhat broader range of frequencies. But Voyager's antenna geometry makes it extremely difficult to resolve that difference with confidence from this distance. Researchers have explicitly noted that a much longer antenna, mounted on some future interstellar probe built specifically for this kind of measurement, would be able to robustly distinguish between these two quantum-rooted explanations in a way Voyager's aging hardware simply cannot achieve on its own. If hearing that the answer to this mystery might require an entirely new spacecraft excites you, that is exactly the kind of frontier science this channel is built to cover. What makes this finding so valuable scientifically goes beyond simply settling an academic debate about wave mechanisms. If this persistent hum truly is quasi-thermal noise, then Voyager 1 has essentially stumbled onto a continuous, passive thermometer and density gauge for the interstellar medium, one that requires no solar storm cooperation whatsoever and could theoretically keep providing usable data indefinitely for as long as the spacecraft's instruments and power supply hold out. Scientists studying turbulence in the very local interstellar medium have already used this steady signal to detect fine-scale density variations that trace the chaotic mixing and energy transfer happening in the thin plasma surrounding our entire solar system, the same kind of turbulence that influences how cosmic rays propagate, and how stars like our Sun interact with the wider galaxy around them. Before this persistent signal was identified, researchers had only ever been able to study this turbulence using widely separated, isolated snapshots taken roughly once a year, making it almost impossible to tell whether any given density spike represented a real physical structure or simply a coincidence of timing. With measurements now arriving every few days instead of once annually, scientists can finally trace how density actually evolves continuously across small patches of space, rather than guessing at the shape of a curve from a handful of scattered points. There is something almost poetic about the fact that the same spacecraft that confirmed humanity's exit from the solar system, using a relatively simple frequency measurement, back in 2013, is now potentially revealing one of the more subtle, quantum-rooted behaviors of matter itself, simply by being patient enough and listening carefully enough to a hum that had apparently been there the whole time, hiding in plain sight inside data scientists had already collected. Voyager 1's plasma instrument was never originally designed with quantum plasma diagnostics in mind. It was built to study planetary radio emissions during flybys that ended decades ago, and yet it has now become, almost by accident, one of humanity's only working instruments capable of probing this exact corner of physics from a genuinely interstellar vantage point, a vantage point that took nearly 35 years of continuous travel to reach, and that no other functioning spacecraft currently occupies anywhere in the solar neighborhood. Voyager 1 currently operates only two functioning science instruments, the Plasma Wave Subsystem and its magnetometer, after years of careful power management, forced engineers to shut down every other system to preserve the spacecraft's dwindling electrical supply. Both instruments run on power supplied by radioisotope thermoelectric generators, devices that convert the natural heat of decaying plutonium into electricity, and that supply has been quietly shrinking by a small, predictable amount every single year since launch, forcing mission engineers to make increasingly difficult choices about which systems stay powered and which go permanently dark. Even its trajectory correction thrusters, last fired in 1980, were successfully revived decades later in 2017. And, again as recently as 2025, an extraordinary engineering feat that has kept this nearly 50-year-old machine alive and transmitting science data far longer than anyone on the original mission team ever expected. NASA's own estimates suggest the spacecraft's power supply may allow it to keep returning basic engineering data until around 2036, though precisely which instruments remain active that long will depend on choices engineers have not yet had to make. Every faint signal it sends still has to cross more than 20 hours of pure light speed travel just to reach Earth's antennas, carrying inside it physics that current theory still cannot fully pin down. If quantum mechanics really does turn out to be the cleanest explanation for that persistent hum, it would mean one of the strangest and most successful theories in all of physics, a theory built originally to explain the behavior of atoms and subatomic particles in laboratories here on Earth, is now helping explain a signal recorded by humanity's most distant machine, drifting silently through the space between the stars. It would be a small, quiet confirmation that the same fundamental rules governing the universe at its smallest scales apply just as faithfully out at its loneliest, emptiest edges, with no exceptions made for distance, darkness, or time. That is the real story behind Voyager 1's plasma wave data, and why scientists are not done listening yet. If unraveling the deepest physics behind humanity's most distant signal was worth your time today, make sure you're subscribed before the next answer comes back from the edge of everything